At the end of the 20th century, European agriculture entered a period of rapid transformation. Farms were becoming larger, harvesting windows shorter, and the pressure on machinery more intense than ever before. In countries like Germany, France, and the United Kingdom, agricultural businesses were expanding into operations covering thousands of hectares. A delay of only a few days during planting or harvesting could affect an entire season's profitability. Traditional tractors, even the most powerful models of the era, were beginning to show their limits. The problem was no longer simply horsepower. Farmers needed machines capable of pulling wider implements for longer hours while maintaining traction on wet soil and reducing downtime between fields. Larger plows, cultivators, and slurry systems demanded enormous pulling force. Yet, increasing tractor weight created new problems. Heavy machines compacted the soil, reduced field efficiency, and placed extreme stress on transmissions and driveline components. At the same time, labor shortages were spreading across the agricultural sector. Farms could no longer rely on large crews operating multiple smaller tractors around the clock. The industry needed fewer machines capable of doing dramatically more work. Efficiency was becoming more valuable than sheer mechanical strength. Inside Claas, engineers recognized that conventional tractor architecture might no longer fit the future of industrial farming. The company was already respected for combine harvesters and harvesting technology, but discussions inside the engineering departments increasingly focused on a difficult question. What if the modern tractor itself had to be reinvented? That question would eventually lead to one of the most unconventional agricultural machines ever built. By the early 1990s, the scale of agricultural equipment had changed faster than many tractor manufacturers expected. Implements continued growing wider and heavier because farms needed to cover more land in less time. Deep cultivators, air seeders, and massive slurry tanks demanded constant traction across difficult terrain. Standard tractors could still perform these tasks, but often at the edge of their mechanical limits. Breakdowns, overheating, and excessive tire wear became increasingly common during peak seasons. For farmers, the biggest enemy was no longer only bad weather, it was lost time. Rain could stop field operations for days, and once the soil dried again, enormous areas had to be cultivated almost immediately. Machines capable of operating continuously for long shifts became essential. Yet conventional tractor designs created compromises everywhere. A longer wheelbase improved stability but reduced maneuverability. More ballast increased the pulling power but damaged the soil. Higher engine output stressed drivetrains that had originally been designed for smaller machines. North American articulated tractors offered one possible direction. Their large frames and central articulation joints delivered impressive traction, especially on huge open fields. But many European farms required something more versatile. Tractors often needed to travel quickly on roads, operate with different implements, and work efficiently in tighter field layouts. Inside Claas, engineers started exploring the idea of a machine that would not behave like a traditional tractor at all. Instead of adapting older concepts, they considered designing a completely new platform around balance, modularity, and uninterrupted power delivery. To many people inside the industry, the idea sounded unrealistic from the beginning. The turning point came when engineers at Claas began to formally document the limits of existing tractor architecture. Internal studies showed a consistent pattern. As horsepower increased beyond a certain range, real field efficiency stopped improving proportionally. More power meant more slip, more fuel consumption, and more mechanical stress on components that were never designed for continuous extreme load. At the same time, agricultural contractors were changing how farming work was organized. Instead of individual farmers owning multiple machines, large contractors began offering full-service field operations. One operator might be responsible for preparing soil, planting, fertilizing, and transporting materials across multiple farms. This shift required machines that could adapt quickly to different tasks without long downtime for reconfiguration. Traditional tractors struggled with this model. Even with the front loaders or hydraulic attachments, they remained fundamentally single-purpose platforms optimized for pulling. Engineers realized that the future machine needed to behave more like a multi-role carrier of agricultural systems, rather than just a pulling unit. This idea marked a conceptual break. Instead of asking how to make a tractor stronger, the question became how to design a mobile power platform capable of supporting different working modes without changing its core stability. That meant rethinking weight distribution, steering geometry, and even operator visibility. Out of these discussions, the first outlines of a completely new machine began to emerge. One that would later challenge nearly every assumption about what a tractor should look like or how it should operate in the field. When the first conceptual drawings of a new machine appeared inside Claas, even experienced engineers questioned what they were looking at. The layout did not resemble a traditional tractor in any conventional sense. Instead of a fixed cab above a rigid rear axle, the design explored a fully symmetrical structure with central operator positioning and equal weight distribution across all wheels. One of the most controversial elements was the idea of a rotating cab. Rather than forcing the driver to work in a single forward orientation, the cab could be rotated depending on the task. This allowed the machine to maintain optimal visibility, whether it was pushing, pulling, or working with rear-mounted or front-mounted implements. For many in the industry, this alone broke decades of tractor design logic. Another unusual aspect was the chassis itself. Instead of a standard rigid frame, engineers explored articulated configurations that allowed the machine to maintain ground contact and traction even under uneven load conditions. The goal was not speed, but stability under extreme agricultural stress. The machine was designed to operate with heavy equipment continuously, often for many hours without interruption. Early prototypes of the concept looked unfamiliar and even unsettling to some observers. It was not immediately clear whether it was a tractor, a carrier, or an entirely new category of agricultural machine. But within the engineering team, there was a growing belief that this unconventional structure might solve problems that traditional tractors could not. What emerged was a platform that challenged the visual and functional identity of modern farming machinery. As the design moved closer to a real machine, engineering work inside Claas focused on turning the unusual concept into a functional drivetrain system. At the core of the project was the decision to use high-output diesel engines from established industrial suppliers, most notably Mercedes-Benz units, commonly used in heavy-duty agricultural and construction applications. These engines were chosen not for novelty, but for reliability under continuous load. Power delivery became one of the central engineering challenges. Instead of relying on a simple mechanical transmission, the design integrated continuously variable transmission concepts that allowed smooth power flow across a wide range of speeds. This was essential because the machine was expected to operate both in slow, high-torque fieldwork and faster transport conditions without interruption or gear shifting stress. The chassis was built around a fully load-bearing frame that distributed weight evenly across all four wheels. This reduced the soil compaction and improved traction, especially in soft or uneven terrain. Combined with a full-time all-wheel drive system, the machine was intended to maintain grip even when pulling extremely wide implements. Another key innovation was the steering concept. The machine used articulated steering combined with coordinated wheel angles, allowing it to maneuver more effectively than its size would suggest. However, this also introduced complexity in control systems and required careful calibration to ensure stability at different speeds. Even at the engineering stage, it was clear that this was not just a more powerful tractor, but a completely different category of agricultural machine. The first field trials of a new concept from Claas took place under controlled but realistic farming conditions. Large European farms provided test fields where soil types, moisture levels, and implement loads closely matched real commercial operations. For the engineers, this was the moment when theory met the physical limits of agriculture. Initial reactions from operators were mixed. The machine's unusual appearance and rotating cab system required a short adaptation period. Experienced tractor drivers were used to fixed forward orientation and conventional controls. Now they had to work with a platform that could change its working direction depending on the task. However, once operators became familiar with the layout, many reported improved visibility and reduced physical strain during long working sessions. Performance in the field revealed both strengths and weaknesses. The machine demonstrated strong traction in heavy soil conditions, especially when pulling wide cultivators and slurry equipment. The balanced weight distribution reduced wheel slip compared to conventional high-horsepower tractors. At the same time, early prototypes revealed challenges in software calibration and hydraulic response under rapidly changing loads. Maintenance teams also noted that the complexity of the system increased service requirements. More advanced driveline and steering systems meant longer diagnostic procedures compared to traditional tractors. However, downtime was offset by the machine's ability to handle tasks that would normally require multiple separate tractors. Despite the early limitations, field data confirmed that the concept was not only viable, but capable of redefining expectations for large-scale agricultural work. Once the machine moved beyond prototype testing, it began to show its real value in extreme agricultural operations, where conventional tractors often struggled. Large contracting companies started using the platform from Claas for heavy cultivation work, including deep soil loosening, large slurry transport systems, and high-capacity seedbed preparation. These were tasks where continuous traction and stability mattered more than speed or simplicity. In wet seasons, the difference became especially visible. Fields that would normally require multiple machines working in shifts could now be handled by a single unit operating for extended periods. The balanced chassis reduced the risk of getting stuck in soft ground, while the all-wheel drive system maintained grip under uneven loads. Operators noted that even when pulling very wide implements, the machine remained surprisingly stable compared to earlier generation tractors of similar power class. However, real-world conditions also exposed the limits of the system. High workload intensity placed significant stress on hydraulic components and cooling systems. During continuous operation, maintenance intervals had to be carefully managed to prevent overheating or premature wear. Engineers responded by refining cooling efficiency and improving electronic monitoring systems that tracked load and temperature in real time. Despite these challenges, the machine proved its ability to function as a continuous work platform rather than a traditional field tractor. It was increasingly treated not as a replacement for existing tractors, but as a specialized tool for the most demanding agricultural tasks where efficiency and uptime were critical. As operational data accumulated, the agricultural industry began to recognize that the machine developed by Claas was not simply another high-horsepower tractor, but a new category of working platform. Large-scale contractors, especially in Western Europe, started integrating it into fleet strategies where uptime and versatility mattered more than traditional machine ownership models. Instead of assigning one tractor per task, operators began rotating implements on a single platform that could switch roles throughout the working day. One moment, it would be pulling heavy tillage equipment, and the next, it would be transporting large liquid tanks or operating wide area spreading systems. This flexibility reduced the total number of machines required on some farms, but it also increased reliance on a smaller number of highly capable units. Manufacturers across the agricultural sector observed these changes closely. Competitors began developing their own high-power articulated tractors and modular carrier systems, attempting to respond to the emerging demand for multifunctional platforms. However, replicating the balance of power distribution, steering flexibility, and operator ergonomics proved difficult without redesigning entire chassis philosophies. At the same time, production costs and complexity limited how quickly such machines could spread. These were not mass-market tractors for small farms, but specialized tools for large industrial operations. Their adoption followed economic logic rather than technological enthusiasm, spreading first where labor shortages and land scale made efficiency gains essential. The impact was gradual but undeniable, as farming operations continue to consolidate around fewer, more powerful machines capable of doing the work of entire fleets. As the concept matured, the broader agricultural industry began to reassess what efficiency actually meant in modern farming. With machines like those developed by Claas entering large-scale operations, the focus shifted away from counting individual tractors toward measuring total field output per hour. This change had deep economic consequences for contractors, landowners, and equipment manufacturers across Europe and beyond. In large farming regions, productivity was no longer limited by the number of machines, but by how effectively a single high-capacity platform could operate without interruption. This pushed farms towards centralized fleets of advanced equipment, where uptime, logistics, and operator skill became more important than traditional ownership of multiple smaller tractors. Maintenance strategies also evolved, with more emphasis on predictive servicing and continuous monitoring systems. Economically, this transition accelerated the consolidation of agricultural services. Smaller operators increasingly found it difficult to compete with large contractors, who could deploy high-efficiency machinery across multiple farms. This led to a restructuring of rural economies, where specialized service providers replaced many independent equipment owners. At the same time, food production systems benefited from more consistent field operations. Faster soil preparation and harvesting reduced losses caused by weather delays, improving yield stability in many regions. However, the dependency on advanced machinery also increased operational risk, since breakdowns of a single high-capacity unit could affect large areas of farmland. The influence of this technological shift extended far beyond machinery itself, reshaping how modern agriculture was organized at an economic and logistical level. Today, the legacy of the concept developed by Claas can still be seen in modern large-scale farming systems across Europe and other industrialized agricultural regions. What began as an experimental attempt to rethink tractor design has become part of a broader evolution in how farms approach power, efficiency, and machine utilization. The original idea was never just to build a stronger tractor, but to create a flexible working platform capable of adapting to multiple agricultural roles. On modern fields, machines inspired by this design philosophy are used in continuous cycles of soil preparation, fertilization, and transport. The emphasis is no longer on a single machine performing a single task, but on integrated systems where one platform can support multiple implements with minimal downtime. This approach has permanently changed expectations for large agricultural operations. Returning to the early test farms, the contrast is clear. Where once multiple tractors worked in parallel to meet seasonal deadlines, now fewer but far more capable machines handle the same workload with greater consistency. The rotating cab, balanced chassis, and high-powered driveline, once seen as unusual engineering decisions, are now understood as practical responses to real agricultural constraints. Yet, the machine also represents a turning point in agricultural history. It highlights the shift from traditional mechanical farming toward highly engineered, system-based production. While not every farm requires such technology, its existence defines the upper boundary of what modern agricultural engineering can achieve. In that sense, the story does not end with a single machine, but with a transformed understanding of farming itself.